Okay, and I already raised questions. What directions the ship is going to kick when the explosion occurs in any place in the water? The ship always kick what direction? As Willie said, the vertical direction. Always ship kicks the vertical direction. Of course, when the explosion occurs right below, it will kick vertically, right? But what about if the ship here, if explosion occurs like that, what direction ship's supposed to kick off? Based on your common sense, ship's supposed to kick what direction? If this is a shock, the explosive is here. So shock wave gonna be hit, then this guy gonna kick that directions. Common sense. Did I say that, right? But in fact, the ship kicks in what direction? Straight up. So that's need explanation. In addition to explain this surface cutoff phenomena. So right here, this is a surface cutoff phenomena. This is 160 psi. This is a pressure versus time. So pressure, this is 160 psi. The R, what's the R? Stand of distance. I want you to really slowly spend the time on my handouts and all that. So 500 feet away, the maximum pressure is 160 psi, and the charge size is a 300-pound TNT in this particular case. So as the R is a stand of distance, that's the distance between the charge and the location that you have interest, or people call the gauge locations or target locations, things like that. So here is 160, so this is R is 500 feet. And this is a surface cutoff effect. And in your note, I usually don't hand out this particular directory. I have a version which has no comment in there. But this year, I just give you the commented version, then you can really see a little bit better. So here I said this is due to the surface reflection wave. Some people call rarefaction wave, or some people call the tension wave. That's what they do. So what happened here is this. I want you to, this is very important phenomena, which is kind of the opposite to our common sense. So then, of course, without knowing this fact correctly, you can't solve one problem in midterm exam. I usually give that. So you need a full understanding. So let's say I have here, this is a charge. And let's say this is a target or gauge. So this is a target. We can say usual name is gauge locations or target location. So this is explosive. Explosive is right there. Or some people call the source. It's all same thing. Okay? An explosion occurs. Then, of course, a shock wave is going to propagate. So incident shock wave path is like this. Incident means it really goes straight out to target. You can think of that way. So if I just draw the straight line here, the first wave which will hit the target is the shock wave connecting the straight line, right? That will hit. So if I just write this is T versus P. And I'm going to say that this distance is R. What's R usually? R is the distance between the explosive to the target or gauge. That's R. Okay? And just the full, I don't know whether I'm going to use it or not, but the vertical distance to the charge, usually I use a capital D, which is a charge depth, right? And the target depth I'm using usually, sometimes I use a different notation, but we don't care. Sometimes, but usually I use a small d, which is a target depth. That's, for the geometry is concerned, that's all you have. And what other quantity you need? Something like C naught. What's a C naught? You should know already. What's the C naught? You know. Acoustic speed in the water. Well, what's the value of acoustic speed in the water? 1500 meter per second. So it's good to remember, which is 1500 meter per second, roughly in feet second. You know, for the design purposes, let's say about 5,000 feet per second is what people uses. But of course, acoustic speed changes, which is really a function of a few different parameters. First parameter, temperatures, right? And second parameter, the salinity. What's the salinity means? Salt content in the water. As salt content is higher, is it acoustic speed is going to be increased or decreased or same? Goes up slightly, but it's not really significant. And another parameter which affects the acoustic speed is pressure. As it goes down to deeper and deeper, then pressure increases. But in the range, the naval ship operate really doesn't matter. Effect is a secondary order. So you don't have to worry about the effect of the pressure to the acoustic speed for the naval, to solve a naval problem. For the acoustics, to solve ocean acoustics problem, of course you have to consider the effect of the pressure, okay? So right now it's a function of temperature and the salinity. So if I just put the P versus the T, until the shock wave hit the target, nothing happened. So this is really right at the target. As I sit here, but explosion occurs already here, but I don't feel it. It takes a time that shock wave hit the target. So what's the time? After bang at time t is equal to 0, how long is it going to take the shock wave to reach the target? This is R, you know the C naught. So it will take some time to get to, let's say T naught. Before I feel the shock pressure, it takes a time, right? Yes or no? Lee, right? What's the time? As a function of R and C naught. You can compute that. What is it? So T naught is equal to R over C naught, isn't it? Elementary school calculations, right? Then, as I sit in the target, then I feel it. Bam! So pressure, shock pressure comes right up. P max. In chapter 3, I'm going to show you how to compute the P max. Things like that. Maximum pressure, which is a function of charge weight, charge size, and what else? Standoff distance, right? Because as the R is getting longer, shock wave pressure is going down, right? So which is proportional to the 1 over the distance, right? Who is missing today? Sungwon, only one is missing. So after that, what happened? As I sit here, bam, to P max, then shock wave passing by, right? So which is exponential decay. Now someone came in. That's great. Yeah. So then it decreases. It decreases, converge to what pressure? Converge to what pressure? It converges into the certain pressure. It goes like that. This is P. So it converges to that pressure, P, what I say here. Shall I say this is PD plus P A. PA plus PD. PA is what pressure? Atmospheric pressure plus PD is hydrostatic pressure. The pressure right up to right here at the target. This is really, I'm considering P here is a target pressure. I'm sitting in a target, right? So converge into the like that. So this wave is called the incident shock wave. Incident shock wave. Shock wave. It's compressing the water. So I'm going to say that the compressive is, I'm going to say compressive is plus. Doesn't matter. You can use a negative. Compressing the water. So let's say compressive wave is plus, then it's a plus. Okay? Then what happened? So some wave will hit the surface, then reflect from the surface, and coming down to the target and hit it. Okay? So this part you need a full understanding. So how do you compute the path of the reflection wave from the surface? How do you do that? Well, it's high school physics or college physics. This is rear explosive. This is a D. I'm going to use this free surface as a mirror. So I'm going to put this is a D, I'm going to put the distance D away, the image charge. This is image charge. Explosive sometimes is called a charge, right? Right? So explosive, sometimes called a source. So it doesn't make any difference. So it's image charge there. So then to compute the reflection wave, which will hit the target first, is you draw the line between the image charge and the target, and then draw this point here. Then the wave which comes through here and hit the free surface, then wave will reflect and come down and hit the target. Okay? Very, very clear. So college or high school, the physics, maybe first year freshman, the physics. So a reflection wave from here, it's a free surface, okay? And then the wave will hit it and come back down here. That's the first reflection wave which will hit the target. Okay? Okay. So distance, look at me here. The distance from here to here is equal to, well, first this distance is equal to that distance, correct? Because this is a D, so this angle is the same, right? Say yes. Yes. So the distance from image charge to the target, I'm going to call that distance as R maybe naught. Okay, R naught. From image charge to the target. Got it? This is worth to explain. If you understand today, you don't have to worry later. But I'm explaining again in early part of chapter 3. So this R naught is the combination of the distance from here to here plus from here to here, which is equivalent to saying that the distance from the charge to here plus that distance, right? So if you look at this triangle here, the one is R, the other one is R naught, which is the addition of the two distance from here to here plus from here to here. Right? So the wave, reflection wave, so will take a little bit more time than T naught, right? Yes or no? In the triangle, addition of the side distance is longer than the third side, right? So it will take a little bit longer. So to do that, so this wave will hit after the incident shock wave hit the target. It will maybe take a little bit later. Not much. We are talking about sometimes a millisecond, sometimes a fraction of a millisecond, because depend on this target depth. Okay? Sometimes later I'm going to say T1. How do you compute the T1? How do you compute the T1? T1 is equal to really R1 over C naught, isn't it? Right? R naught is that distance plus that distance, right? You can compute the T naught. What does it mean T naught? Right at time T naught is measured from here. This is T naught. T1, T naught is measured from there. Okay, so the surface reflection wave is concerned. From here, when the shock wave hit here, right there, this is a compressive wave. I'm going to say plus, compressing the water. But as you would see U571, you will see the plume right after explosion within the few milliseconds. Then you will see the plume. Water particles shoot in the air because there is nothing to stop right at the free surface. All the water particles shoot upward direction. So as you look at if you look at the particle, it's going to come straight up. But right here, reflection wave is coming down. This portion is a problem area. Well, not the problem area. This is a compressive. This portion is not compressive, which is tensile. What does it mean, tensile? Think this as attractive source, okay? This is attract the water particle. So here, this will reflect. The wave reflect, but this is attracting. That's the easiest way to solve, easiest way to understand the physics of it. By the way, the incident, through the incident shock wave, what happened? Water, if you think this is a water particle, it's going to shoot in that direction, right? Water particle will, by this wave is coming straight out, water particle will move in that direction. But if you think this is a ship, if this is a CG of the ship, okay, when the explosive is here, when shock wave hit it first, this guy will move in that direction. If this guy, if you assume as a water particle, is going to move in that direction. Is it clear? Yes. But physics doesn't work. Not only that component, you have additional component such that think this is as image charge. All the water particle is moving toward the image charge. Toward image charge. Okay? When you become age of 18, it's a teens, okay? When you look at the, this is in the video clips, not the video. You know, it's all attracted by the beautiful, the other teens. So all this is water particle is moving toward the image charge. Water particle is moving by the image charge, but at the same time, the acoustic wave will move what direction? Opposite direction to the image charge and moving toward the target. Do you see that? You have to see that. So this portion, water particle is shooting toward the image charge, water particle, but shock wave is moving opposite to the direction of the water particle. That is called the tension wave. So tension wave, so this portion, this is a tension wave, this portion. This is a tension wave. Tension wave. It's worth talking for 30 minutes and more. Tension wave, sometimes called the rarefaction wave. Rarefaction wave. Or surface reflection wave. It's all same thing. Tension wave. So water particle is kind of the water density around there is getting sparse because you try to pull the water particle out. That's why when you look at the plume at the time of explosion, plume's usually white. Why? Due to the tension wave effect, water particle is kind of the split. Rather than compress, it's take apart. So its plume is concerned, the water density is kind of getting much lower. Okay, so if I put it here, so this is now the negative pressure, not the positive, negative. Shock wave is coming down toward the target, but water particle is moving toward the image charge opposite to the target. So if I draw here, so I can draw like this. And now it's gonna go approach. It could go it could go something like this. And this is the P max due to the image charge. Of course, this, I'm going to say P naught, okay? This P naught is much lower than P max because it's the standard distance to image charge, R naught, is longer than the R. So now the resultant pressure goes like this. At the beginning is like this, then straight up, then coming down. When target experience the tension wave, then it cuts. So you can just add together. This guy, look at me, this guy, this much pressure plus that. Okay? So if I just add it together, it could come below absolute zero, below zero. However, water cannot sustain the tension. Water cannot sustain the tension. Water can sustain maybe 3 or 4 psi. PSI means a pound per inch square. You can convert into the megapascals, whatever, okay? So 3 or 4 psi. The atmospheric pressure is about 14.7 psi. So even you can feel it, okay? So if you come down to, when you add algebraically this tension wave with the compression wave, incident shock wave pressure, and tensile wave pressure, it could go down here, but you can't go down far below. It could go just 3 or 4 psi, maybe it could go around there. Then you have to keep adding this guy. Then it drifts just below zero. Then what happened? Then it's gonna merge right there. Right there. Because P naught, PA plus PD, it happened to be there, has to be there. Okay? So it's gonna go like this. something like this, as a resultant pressure wave. But so this is a negative. This is negative means tensile pressure wave. So if you have, for example, down here, this is C bottom. C bottom. Then what happens? It will, when the shock wave hit the C bottom, so of course it will reflect. So I'm going to put the distance from here to here, the same distance, I'm going to put it here, okay, as another image source. So not that distance. That distance, you can think this as a mirror image, then that distance to same distance over here. Then you can connect to this guy there. So reflection wave from the bottom, which will hit the target, is in that path. This is a compressive wave. This is not the free surface. So reflection, when the reflection occurs, this wave is also compressive wave. So it's going to hit the target there. So there will be the additional compressive wave, which means it could come, then depend on the depth of the ocean, it could, another wave could hit, vice versa. I want you to understand what's happening there. Is it clear? Very clear. I think I explained pretty good, so not bad at all. Next is scaling law, principle of similarity. Chapter 4, I'm giving you more the extended version based on Hopkinson's scaling law, but this is give you some good appetizers, okay? So as you see in the note, I want you to carry always my handouts. It said, if the linear size of the charge has some meaning, is changed by a factor of K, the pressure condition will be unchanged if the new distance and time scale K times as large or as small as the original ones are used. For example, mg is a charge weight, right? mg is a charge weight. Look at my cursor. W, charge weight, that's mg, is equal to rho, mass density of the charge, v is a volume of the charge, and g, gravitational acceleration. mg is rho v g. So g is a constant, and m is proportional, the rho is a constant, and mass is proportional to the volume, right? So volume is length cube, right? If you look at as a unit, length cube is a volume. So volume is proportional to length cube. If I say length is a K, is change the linear size of the charge, linear size, not the volumetric size. So which means it's a K falls right here. You got it? Got it? Yeah. So K cube. So if the volume, reduce the charge size, which is V, by a factor of 8, the linear size of the charge K is 2, right? 2 to the cube is 8. You got it? Yes. Yes. So if volume is 8, if the charge size is reduced by a factor of 8, which means linear size of the charge is a factor of what? 2, right? 2 to the cube, right? Lee. Clear? Hassan? Clear. So if if you see the charge size is 27, so K cube, K is 3. The whole idea for principle of similarity is, well, rather than I use 1,000-pound charge, 1,000 kilogram charge, I want to reduce the charge like a factor of 1,000 to save money and time. So that's the idea, to reduce the size, then use it. Okay, everything has to scale down. So here is one quick the example. So now the K is 2, and this is, let's say, 300-pound TNT. Okay, 300-pound TNT. And then this is previous page. You can see for 50 feet is a 2200 psi, and the K is a factor of 2. So what does it mean? What does it say here? The pressure condition will be unchanged if the new distance and time scale K times as small as original ones are used. So the K is 2, you have to reduce the distance and time by the factor of 2. So divided by D by 2, the T divided by 2. So you will get the same 2200 psi. If you use a 37.5, you can use 37.5 pound TNT, then still you can achieve the same 2200 psi. However, you have to slice the D by the factor of 2. Okay? So rather than using that distance D, you have to divide it by 2, because linear size of the charge is K is 2. Do you follow me? It's not difficult. Okay, similar to the rule. So the original charge size is this is a volume times rho G. So 300. You have to divide it by factor of 2. No. This is a volume, so you have to divide by a factor of 8. All others quantity, time and the distance, then you will divide by a factor of 2. So this is like a prototype. You call the prototype, and this is for model testing. For prototype, 300-pound TNT. But for the model testing, you can reduce the size of the charge to 37.5 pound. But to get the same shock wave pressure, you have to slice the distance and time by a factor of 2. However, peak pressure is identical. However, the trailing pressure is not the same. You can't win them all. Look at that. So the trailing wave is much fatter than this. But at least the shock wave pressure, maximum pressure, is the same. And this is in changing increase. In this case is decrease, so that's the case. Okay, next I want you to read all this phrase. I went through this last week, so I want you to really read. One thing I want to comment here is this is all gas bubble motions. For the gas bubble motion, maybe as time permit, I'm going to show you my students' work toward the thesis, the gas bubble oscillation and gas bubble motion is moving toward the free surface and venting out. I'm going to show you that also as time permit. But this is a free surface, and your explosive could be down here. Then of course when it oscillates, it will migrate toward the free surface because of the buoyant force is there, right? Then how many cycles bubble gonna grow, bubble gonna reduce down to minimum, then lose the balance, then it collapses. Whenever bubble collapses, inside the bubble there is energy, explosive energy is still there, but at the same time as it oscillates, the energy radiates into the water. So it losing the energy, not losing everything in one cycle. As it migrate, moving toward the free surface, energy losing it, size of the gas bubble is slowly growing. But how many cycles? It would just depend on depth, right? Depend on the depth of the water, then it changes, right? So it's gonna sometimes 2 cycles, sometimes 1 cycle. If it's deep in the water, then it will take a little bit more time. But as it move toward the free surface, energy could be almost all wear out, could be gone. So when it really venting out into the air, then plume size may change also. Then you will see the plume size and all that. I have all the video clips. So from time to time, you will see the video clips and all that to get the feel of it, okay? But bubble, that's the killer. Not only shock wave, which carries how many percent roughly? About 52, 53%. Then the other energy is carried out by the bubble. Inside the bubble, confined by the water, there is all that the energetic, the gas product, which has a tremendous the energy in there. So once, for the Tyson, the boxer, he hit it by the one heavy punch. The other guy didn't knock down. Usually they don't knock down. They just after hit by the Tyson. You know Tyson? Well, I don't know who is now a heavyweight champion. Bang! Short guy, really. Then the other guy almost don't know where he is. Then what happens? The bubble collapse. Shock wave, bang onto it. But still ship is there. But second blow is by the gas bubble. Bang! As it come down to the minimum. Bang! The secondary shock wave. Hook. One punch. And bubble motion is a hook. Small hook will kill it. Small hook. Cheonan naval ship has 2 pieces and just sunk. That's what happened. So both are so important to know, and that's the very fatal excitation mechanisms. And the bubble oscillation period This is kind of the empirical relation. T is period of oscillation. What does it mean, period of oscillation? This is gas bubble oscillation. What's a period? Gas bubble grow to the max, right? Then get down to the min. One cycle, one period, right? One period, there's a T, there's a time. So time, then what's the frequency? Time, you compute the time there, T is equal to over there. Then now you can determine the corresponding frequency, which is 1 over T. If the period is 1 second, then what's the frequency in cycle per second? 1. 1 cycle per second. 1 over T is 1 over 1. What happens if the time is 2 second oscillation period? Usually the period, well, could change depend on the depth of the charge. It could change it, charge size. And if it's 2 second, corresponding frequency in hertz, you know about it. What's the hertz means? Cycle per second, right? So in terms of the frequency is what? 0.5, because it's 1 over 2, right? It's 0.5 hertz. So pretty low. I'll tell you a lot more on it relate to whippings and all that. And there is this is a time axis. Horizontal axis is a time. And the first maximum, this is second maximum, first minimum, and second maximum. As it oscillates, minimum size of the bubble is growing because energies keep losing. Usually that's what happens. And this is for 300 pound TNT charge, and this is a free surface. And if you look at the slice, vertical slice, is the bubble size at that particular time. And this is charge location. And the center, this is a trace of the center of the bubble. Bubble is growing large as it migrates toward the free surface, this down to min. So this distance is like the diameter of the bubble. And it goes up and up eventually, the venting out. Okay? And here, this is empirical, the equation done by the experiment. So here, this is a T. This is a unit dependent, okay? This is a period of gas bubble. And this is for TNT. That factor is based on the charge type. For TNT, in chapter 3, I gave you the table. For the charge type, then this value changes. W is the charge weight, which is equivalent to TNT. For example, HBX1 is much stronger, 50% stronger than TNT. To get the W is equivalent TNT charge weight, okay? So if you have 100 pound HBX1, which is equivalent to the 150 pound the TNT, because factor, the multiplier, is about 50%, 1.5, okay? So anyway, this is a charge weight in pound. Then D is charge depth. You know, you have to put the charge at certain depth. That's a D. Plus 33 is equivalent hydrostatic head of atmospheric pressure. Equivalent hydrostatic head. You have to add into it to the charge depth. How the 33 came in? This is all unit dependent. W is the pound. That's in pound, okay? And T is in second. D is in feet. In Europe, they convert everything into metric. And here in Korea, just use as is. Then after you compute that, you know, to compute D in feet, you know the meter, how many meters of charge depth. You know, you can convert into the feet, you can convert into the pound, right? 1 kilogram is something like a 2.2 pound. You can convert, and you can get that. So T is period. R is radius of gas bubble. So don't confuse R I'm using as a standoff distance. R here is the radius of, maximum radius of gas bubble. You need all that. This is very important parameter, as you will see later. And this is a factor for TNT. For other charge, you have a different value. You will find in chapter 3. How to compute 33? 33 is 14.7 psi is atmospheric pressure. Times 144, convert the inch to pound, the inch to feet, inch square, so that's a 12 square. Then you have that times D. D is equivalent the hydrostatic head. It comes out about 33 feet. I want you to re-examine there, okay?